nanohub.org.
Online simulation, and more for nanotechnology.
Hello, everyone. Welcome to this latest nanoHUB webinar. So this particular webinar is again from Schrödinger. It will be a hands-on demonstration of machine learning models for ionic conductivity with Schrödinger's AutoQSAR. So the speaker, the presenter today is Dr. Michael Rauch, who is a principal scientist one at Schrödinger, specializing in material science and education. Michael received his PhD from Columbia University in synthetic organometallic chemistry as an NSF graduate research fellow. Then Michael was a Zuckerman postdoctoral fellow at the Weizmann Institute of Science, where as a postdoc. Michael's interests particularly lie in green and sustainable chemistry and transforming the way that synthetic chemists utilize molecular modeling via practical education. So with that, I believe, Michael, why don't you go ahead?
Thank you so much for the kind introduction, and thank you, nanoHUB, for allowing us to deliver this two-part seminar series. Today's session, I'm going to give a couple minutes of slides, and then I'm going to pull up nanoHUB itself and walk you through an actual hands-on example of using Schrödinger's machine learning tools, specifically for developing models for predicting ionic conductivity of ionic liquid materials in the sort of like battery application area. So just going to take a couple slides for anyone who's unfamiliar with Schrödinger to sort of remind you what we do as a company, particularly in the material science space. So Schrödinger has two main products in the material science area. One of them is called Material Science Maestro, shown up here on the left, and the other is Material Science Live Design. Material Science Maestro is a single platform for building models, running simulations, predicting properties, and analyzing data. Live Design is an informatics cloud platform for collaborating, designing, and so forth. And our MS platform that's shown here on the left is sort of commercial grade software for atomistic simulation and machine learning. And so at Schrödinger, we work in many areas. And so the types of chemical systems that we work with range all the way from molecules and complexes to, say, polymers or really complicated blends. And we take these molecular systems as sort of building blocks in the various applications shown here on the right. So for instance, we have a long history of using atomistic simulation for organic electronics capabilities in the areas of polymeric materials. And the example that we're going to touch on today comes from the area of energy capture and storage, where predominantly our work is in the space of atomistic simulation and machine learning for the discovery and understanding of battery materials. So these are the types of systems we work with. These are the sort of industries or applications that we tend to focus on. And these are the methods that we have capabilities for in the Schrödinger suite. So again, it's one interface that taps into all of these methods. So we do molecular quantum mechanics with our engine called Jaguar, predominantly DFT, but also all sorts of semi-empirical methods. We do periodic quantum mechanics through a partnership we have with Quantum Espresso. We do molecular dynamics and coarse grain simulation with our back-end engine called Desmond. And then what we'll be talking about today and what Anand spoke about today is we also do data-driven simulation, particularly machine learning. And the main tool that we use in that space is called AutoQSAR. We have a second tool called Deep AutoQSAR, which we won't be covering today, but is also worth looking into if you're interested in our capabilities in that space. And so what we do at Schrödinger is we take these underlying methods and then we build workflows on top of them. And the workflows allow scientists to sort of efficiently execute simulation type workflows. And so in the space of machine learning, the types of workflows that we offer are rapid descriptor generation, built-in property prediction, predominantly through those QSAR tools, and we also have capabilities for active learning. If you're interested in the type of work that Schrödinger does, we have a blog. It's called Extrapolations. You can search for it and you can read all sorts of stories from different, mainly industrial customers who are using our tools to drive their R&D. Okay, so today in about 1 minute, I'm going to open up nanoHUB, and the example that we're going to cover, sort of, looking back at those earlier slides, it's going to merge molecules and complexes, the area of energy capture and storage, and the method of machine learning. And we're really pleased that in the past, I think it's been over a year now, but Ali and I would have to check, we've forged a really nice partnership with nanoHUB where we've made, in particular, some of these tools for machine learning available in nanoHUB. So right now, the only capabilities we have available in nanoHUB are just a couple of examples for machine learning. But certainly if people are interested, we'd love to hear, what sort of tools would you love to get trained on and learn to use from Schrödinger. You can chat in the group forum that we have up on nanoHUB, and we can talk about in the future adding additional capabilities for learning, training, and sort of exposure to what Schrödinger has to offer. So the specific example that we're going to go over today is taking a data set of about 400 ionic liquids from a NIST data set, which have reported ionic conductivities. And so we have SMILE strings for all of those structures. The entire data set was taken around room temperature, plus or minus maybe 5 degrees, and we have ionic conductivity values that are experimentally known for these structures. And the idea is that perhaps ionic liquids could be considered for battery electrolytes, but one of the main drawbacks in using ionic liquids is that they don't necessarily have high enough ionic conductivity. And so what would be interesting would be to take these ionic liquids and develop a machine learning model that we could use to predict ionic conductivity. That may allow us to design additional ionic liquid structures that we could use in battery systems. And so first, we're going to learn how to actually input all of that data into the interface in nanoHUB. And then we're going to use the AutoQSAR tool that Anand described last week to build a model, look at the quality of the output model. And then we have a holdout data set that we're going to pull in to the material science Maestro interface in nanoHUB and actually use the model to make predictions on ionic conductivities. And that holdout set we also know the experimental values for, and we'll show you how you can plot and see the quality of the predictions. So I won't go into it in any detail right now because Anand covered it last week, but the engine that we're going to use to build the machine learning models today is called AutoQSAR. So AutoQSAR is an automated tool that takes in structures and a property to be fit, and it automatically generates hundreds of descriptors, fingerprints, decides which of them should be used towards developing models. It can handle categorical or continuous data. It does train and test splits to generate a series of models. It maintains many of those models so that it can do property prediction sort of with a ensemble of those outputs. And it also allows you to then generate additional models built on top of that. Okay, so now we're going to actually go into nanoHUB. So there are 3 things you need to do in order to follow along in today's hands-on portion. So the first thing you need to do is you need to have a nanoHUB membership. And with your nanoHUB membership, you need to request to join the Schrödinger group. So the tool is not available to anyone who's not in the Schrödinger group on nanoHUB. So please join the group. Once you've joined that group, you want to go to our tool, which is called Schrödinger Material Science AutoQSAR for Machine Learning. The link is here. So if anybody is already a member of nanoHUB, a member of our group, you can go straight to this tool/AutoQSAR. And then once you're there, we're going to launch the tool. I've already joined the Schrödinger group. And so here I'm on the tool page for Schrödinger's AutoQSAR tool. And again, you can get it with this link up here, /tool/AutoQSAR. And so on the about page for the tool, you can find all sorts of information. You can find links to different Schrödinger products. We have some videos about our online training offerings and some major publications that we've published in the last several years, particularly using AutoQSAR for machine learning. And the one thing I want to point out on this tool page before we launch the tool is that if you go to the supporting docs tab, that's very important. We have 3 tutorials which are available which have preloaded data in nanoHUB such that when you launch the tool, you'll be able to work through all of these. So today's example is here. And so if you're following along and you get stuck, you can, of course, watch the recording later. We'll share it on nanoHUB, but you can also come back here and just execute the tutorial on your own time. There's also all sorts of information in that tutorial that I may or may not cover as I work through the example. In addition to this tutorial that I'll cover today, there are 2 other examples available for anyone who's interested in exploring the tool a little bit further. This one, Machine Learning for Material Science, it's a data set of Tdaf molecules for organic electronics applications, where we build machine learning models to predict delta ESTs for those structures. And then the third example here on the bottom is a set of, I believe they're iridium catalysts with known reaction rates for a sort of photochemistry reaction. And we teach the workflow for how to take that set of organometallic complexes with known reaction rates for one specific transformation and build a QSAR model, which you can use to then design new catalysts. So the data sets and the tutorials for all three of these examples are available in nanoHUB. And these are available for you to use for your own training. They're available to use for teaching. So if anyone on here is a professor teaching a class in material science, if any of those align with the sort of material that you're teaching, feel free to use these. And if these topics are not the specific topics you'd like to see, again, use the forum, use the chat, let us know the types of content you're interested in, and we'd be happy to discuss adding more content into nanoHUB. So with that, we're gonna follow this tutorial in the middle today, but I'm just gonna launch the tool and we'll work through it sort of live together. So you will have to accept the EULA to use our software. And when you do so, the software should immediately launch in the nanoHUB window. Take a moment and note that Schrödinger releases our software every quarter. So this software version that you're using in nanoHUB was the last release from 2022. So there have been actually 3 more releases of the software since then, but all the capabilities you need for this exercise are available here. So this window that's open, this is called Materials Science Maestro. So this is our graphical user interface, which again is not just for machine learning, it's not just for battery materials, it's for all of the types of models that I described in those earlier slides. It's for all of the application areas that I described, and it has engines underlying it for all of those methods, again, all the way from quantum mechanics to MD to machine learning. And so this is the same interface that we use for all of those capabilities, but today we're going to use it specifically for this machine learning exercise. So now the first thing you should do is you should assign a working directory. So this is just a way to point Maestro, which is our interface here, to the folder where all of the data that you're going to need for this exercise are. So first do File, Change Working Directory. And if you go to the Home directory here on the upper left, we have available for you a Schrödinger folder. And if you open that Schrödinger folder, you can just click once on the ML Ionic Conductivity folder and click Choose. And that will set that folder as your directory. I'll show that one more time. I'm going to do File, Change Working Directory. I'm going to go to the Schrödinger folder, which I can access using this Home Directory button on the left. I'm just going to click this ML Ionic Conductivity once, and then I'm going to click Choose. And note that these other folders here, those are associated with the other 2 tutorials that I was describing. So if you're interested in trying out those workflows later, you can definitely go ahead. Okay, so I've assigned the working directory. The next thing I'm going to do is just save a project. So saving a project more or less saves your instance of Material Science Maestro. And actually, you could come back and open these projects later with the way that we've set everything up here, thanks to nanoHUB. So you can click Save Project As, and you want to name the project whatever you like. And so I'll call this Ionic Conductivity Demo. And your folder may look a little different than mine because I ran a test this morning just to make sure everything was working well, but you should at least be seeing the Section 3 and Section 5 folders there. And so I name my project and I click Save. Okay, so those are sort of like the 2 bookkeeping things we need to do. We need to set a working directory and then save our project. So now we're going to import that data set that I described earlier. So we had about 400 ionic liquids, and we've separated into a data set that we're going to use to actually train AutoQSAR. And then we kept a holdout set that we can use later to test the quality of our models. So let's first go ahead and import that data. And so the way to import that data is to go File, Import Structures. And if you set your working directory properly in the previous step, this should open automatically in this working directory folder. And the data set that you want is this train data set. So it's fixed_temp 298k train.csv. So this is a CSV file. I'm going to show it to you in another window in a moment, just so you can see, but this is stored in nanoHUB for, again, use for this tutorial. And so when you click Open, it's going to tell you, okay, this is a CSV file. It has 353 rows and 4 columns. Which columns do you want to use to designate the smile strings, which is how we're going to actually generate the structures? And what do you want to call each entry? So in this case, the smile structures are in a column called smile in the spreadsheet. I'll show it to you in a moment. And let's name them by their index. We can name the structures anything. If your CSV has molecular names or something like that, you can assign that column. And then make sure you don't discard the additional properties because we're also importing the known ionic conductivities of these structures. And then click OK. And so what should happen is you should see a whole bunch of structures come in on the left here. I'm scrolling. There's about 353 structures. I'm going to show you how to look at them in a second. But before I do that, I have open here in another window the data that we just imported. So this is what the CSV file is that we just loaded in to Material Science Maestro. So it has 353 structures. They're designated by these indices, which are just from the NIST database. But then we have the smile strings, right? So for those not familiar, smile is a 1D representation of a molecule. We have the temperature, which we don't need, but this is to just show you that we trimmed this set down to all similar temperatures. And then here's the ionic conductivity value. So, right, to develop a machine learning model, you do need some input property for known structures, which you're going to use to build out your model, right, for your unknown structures. And so these values are experimental, and whatever machine learning model you're looking to build, be it with AutoQSAR, you're going to need both of these things, structures and a known property in your data set. You can have additional properties, which you could consider using as descriptors. And so we're not going to show an example of that specifically today. But if you had, some additional experimental data on all of these structures and you wanted to use that not as your property to predict, but as additional descriptors, you should make sure your CSV file has those as well. And you can pull them into Maestro. And I'll show you how you may, add those in to your model later on. So let me go back here to nanoHUB. And so down the left here, we have what's called the entry list. And this shows you all of the structures that we just imported. So whenever a blue circle here is filled, we say that that's the included structure, and that's the structure that you're viewing here in the workspace. So one thing to note is that these smile strings, they don't come in with known hydrogens, and that's okay. AutoQSAR will automatically account for that. If you were going to go run DFT calculations on these structures as well, then you'll need to account for that. And Schrödinger has tools and capabilities for addressing those hydrogens. But note for AutoQSAR and building machine learning models, you don't need to worry about the implied hydrogens. So if you want to look at other structures here, you can just work through the entry list, filling in these blue circles, and that changes the included entry in the workspace, which you can look at over here on the right. And so you can see the series of ionic liquids. They have a variety of structures. Some of them have just 2 components. Some of them, I believe, have as many as 4 components. And there's a mix of the types of cations and anions that we see in these structures. And we'll look at the domain space a little bit afterwards. Okay, so just to show you where that data actually goes, because I mentioned we imported that spreadsheet, you can click Table, which will open what's called the project table. And you can bring it, you can extend the screen a little bit. And if you want to view all of the properties, so this table maps onto the entry list on the left here. So if you want to look at any data that you loaded in, you click this button here, which pulls up the property tree. That allows you to add or subtract the properties that you're seeing in columns here. And you can go to Canvas, Secondary, Ionic Conductivity. And so if I check that off and I scroll over, here are my ionic conductivity values from that CSV sheet, right, all associated with the different entries down here on the left. This is just to show you how that data sort of gets pulled in to Maestro. Okay, so now we're going to use AutoQSAR to build our model. So we want to build the model on all of these structures. A useful thing to do is to just group all of them. So like right now, they're sort of each standalone entries in this entry list. So to group all of them, we need to highlight them all. So you can do like a shift click on every single line here in the entry list, and then right click on any of them once they're all highlighted, and click this group button. And that allows you to create like a collapsible group over here in the entry list. And so we're going to call this group the training data, because this is the data that we're going to input as our training data for our ML model. So I'm going to click create group. And all I did there was just make it so that this group is like collapsible and all selectable at the same time. So we're going to build the ML model. We need to select all the structures that we want to use for the ML model. And so this filling in these circles, that's how we view the structures, but highlighting them is how we call upon them to be used in the next step, in this case, the AutoQSAR step. So just make sure you click on your whole group so that everything is highlighted. And then come up to the tasks menu up here. And this is where you can find all of the different tools that are available for Schrödinger. So I mentioned we don't just have machine learning tools, we have builders, quantum mechanics, etc. But for nanoHUB right now, the only tools that we have licenses for are just using the AutoQSAR for these educational and training examples. Again, if people are interested in learning more, we can talk about options at the end, and we'd be open to adding some additional functionality into nanoHUB. So the tool that we want to use is AutoQSAR. So the way to get there is to go tasks, materials, informatics, and then open the AutoQSAR panel. So I click on that and it will pull up the panel. It may take a moment to load. Looks like it might have loaded in the background. If that happens, just click down here on the tab and bring it forward. If you're having trouble finding it, there's also a search capability up here. You can literally search for AutoQSAR and you'll find the panel. Okay. So this is our tool for automated construction of ML models. So it's also the same tool that we use to view the output and to make predictions. So first thing you want to do is make sure, in this case, we're on the build model side of the capabilities, because first we're going to build our ML models. So then you tell it which structures to use, because you may have more structures in this project. In this case, we just have this imported 352 structures, and those are the project table selected entries. So just make sure this says use structures from project table selected entries and that all 352 of these are highlighted. Now the property to be fit, again, this is one of the properties that we imported from our CSV. It's the ionic conductivity value. You can see, there's other sorts of properties associated with these structures. If you imported with a different property to be fit, you would just choose it here from the dropdown. You then need to specify whether this property is numerical or categorical. So AutoQSAR can handle both. In this case, the ionic conductivities are numerical values. So it's a regression task. So we just select numerical here. And so now what AutoQSAR is going to do is it's going to do a random split of these 352 structures, and it's going to hold some out to use as a test set. And so you can set the percentage of structures that you want to be used in the training versus the test set. So with about 350 structures, it's okay to take this training set size to say like 90%. So we'll train on 316 of the structures and we'll test on 36 of the structures. This depends on, do you have 10,000 structures or do you have 50 structures? In this case, 350 is a good amount of structures. We can train on 90% and test on the other 10%. And then I mentioned we can do like consensus prediction depending on how many models we keep. And so here you can choose how many of the ML models that get output you actually want to keep from the calculation. And so in this case, we'll keep 10 and we can use all of those to do consensus prediction. So if anybody is sort of behind, what we've done is we've imported the structures. We just had a look at them in the workspace, but we didn't do anything with them yet. We put them in a group just so we could highlight them all very easily. And then I went to the tasks menu and we pulled up the AutoQSAR panel. We opened AutoQSAR, we chose build model. And the only change we've made in the options here is just to pick a 90-10 split. Now there are other advanced options here. So this is useful because you maybe want to use other properties. So I mentioned you may have like a spreadsheet where you have other experimental data that you want to use as descriptors. You can call on them using these advanced options. In this case, we're going to keep all of these defaults. This is going to use binary fingerprints, numeric descriptors. It's a couple hundred descriptors that are going to get generated automatically on the back end, and those are going to get used to generate the ML model. So I don't touch anything here, just letting you know that sort of this is what's happening behind the scenes and that there's capabilities to add additional properties as you like. So now we'll name the job. We can call this one QSAR underscore build underscore train. And we're going to run this calculation locally through nanoHUB. And it takes about 15, 20 minutes. So we have the files for you as well. So we're not going to wait for it to finish. But if you're interested while you're here in actually running the job and seeing the data come back, just open this gear here. And when you open this gear, you can choose the host. And so you see we have like 28 processors available in nanoHUB. You can use one processor, two processors. I think I ran the calculation with 6 processors, took about 15, 20 minutes. Click save, and then push run to run the job. So I'm not going to launch the job myself because I'm going to proceed with data that's already run. But certainly you can run the job, and you should run the job. And if you're using this for teaching, having students run the job is a great thing to do. So once that's all set, you would close the panel, and you'd wait for the calculation to finish. So we've already run the calculation and we have the data available. So I'm going to show you how to actually view what would come back like 15 or 20 minutes later from this calculation. So first, you go back to the AutoQSAR panel. So if you missed how to get there, you can go to Tasks, Materials, and then the Informatics set of panels here, and you open back AutoQSAR, or you can search for it. It looks like, just so people know, every time I open it, it seems to open behind my window. And so if you want to pull it forward, you just click on the tab down here. So here's AutoQSAR that we just used, but now we're going to switch to the view model and make prediction capabilities. So again, after your calculation finishes, and by the way, you'll know your calculation finishes because we have a job monitor up here. It will turn green while the calculation is running. You'll see like a green circle there. And then as soon as the calculation finishes, you'll see a green check, and like a banner will appear on the top of the screen letting you know that your job is finished. So that will indicate to you that you could proceed to this step. You can also just proceed directly to this step because, again, the data is available for everyone in your nanoHUB instance. So we go to View Model and Make Prediction. And what we have to do is grab the file that comes back from the calculation. So you click Browse. And again, if you set your working directory correctly, at the beginning of the exercise, this should open in that folder. If you ran the job, you would see the folder for the job that you ran in here. If you didn't run the job, like in my case, you go into the section 3 folder, and you'll see a directory, which is actually the output directory from running the job previously. I'm going to open that, and inside there's a file, which is a QZip file, which contains all of the output data from the AutoQSAR job. So let me just show you that again. If you open up Browse here in the AutoQSAR panel, it's going to open your working directory. You go into section 3, where we have provided data, into train AutoQSAR, and you click Open on this QZip file. Okay. So when you click Open, the panel is going to update, and the first thing it's going to do is it's just going to show you the score for the models that it generated. This is the consensus score from the full QZip, but if I click plus, it's going to pull up a table here. And this table shows me that in this case, we asked for the top 10 models. So these were the top 10 models that were generated by AutoQSAR, again, in about 15, 20 minutes with no need to specify any descriptors. They're all taken care of on the back end. And so in this case, almost all the models that come back, actually all the models that come back for this example are KPLS type models. And so if you do the other 2 examples that we have tutorials for, you don't always get just KPLS type examples, but in this case, those seem to work the best for these ionic liquid structures. And so for each model, you can see a score, you can see a Q-squared value. If you click this Show More button, you can also see like R-squared and RMSE values. And these are the values relevant to relative to the holdout set, right, which is the 10% of the data that AutoQSAR randomly set aside when building these models. So now for each of these models, you can highlight the row. So for instance, let's take the top model that came back. It's this KPLS dendritic 38 model. And you can look at 2 additional pieces of data. So one thing is you can click on the report details. So the report details is actually going to show you the output data for every single structure, right? Whether it was in the training set or at the bottom, the test set. it looks like they're mixed in, the training set and the test set. You can see how they were randomly split. The observed and predicted values, the error, and then the, again, R squared, RMSE, and Q squared for that model. And if you click on scatter plot, you can see the scatter plot here for predicted versus observed for both the training set and the test set, where the blue points are the training data. Again, it's about 330 of the structures, and the red points are the 10% from the holdout set. And you can see, in this case, obviously, it develops quite a good model right off the bat here out of the box with AutoQSAR. So let me close that, and I'll close these report details. But you can feel free to look at the report for any of these top 10 structures and see how the scatter plot looks. And you can use just one of these structures to make predictions or the consensus. I'll show that in the final stage here. But before we do that, there's one other capability, particularly when you have KPLS type models, which is one of the reasons we chose this description, which is one of this example, which is if you click this other button here for visualize model, it will open for you a 2D viewer where you can actually see the atomic contributions to the model. So this is a nice way to get some sort of qualitative and quantitative feel for sort of like which maybe functional groups or atoms are contributing positively or negatively towards the ionic conductivity. So I believe that the blue disks indicate a positive contribution, the red disks indicate a negative contribution, and the sort of boldness of the fill indicates the magnitude of the contribution. So you can see like, this like quaternary ammonium salt seems to be a good cation to consider compared to this borate salt. But maybe these like TFSI type anions are sort of okay, but you could scroll through and sort of like get a feel for maybe, what kinds of moieties seem to be really helpful in driving ionic conductivity. So this is useful for design, right? If you want to then go in and try and sketch some new ionic liquid candidates and then predict their ionic conductivities, you can use this again, qualitative and quantitative information to drive that design. So this data is available, again, for each model that comes back. So that's just the first model, but you could go to the fourth model. You could look at its report details. You can open its scatter plot. You can see the quality of the fit for the training and the test data. And you can also visualize those, the fingerprints here. Okay, so that would be the first step in building an ML model with AutoQSAR would be to have your data set, load that data set into Material Science Maestro, open that data set with AutoQSAR, run a calculation with whatever parameters you want to specify, and then look at the quality of the results and decide if you think that the models that you generated are high quality, which in this case we can clearly see that they are. So then the next thing you might want to do is take another set of structures and use your ML model to predict ionic conductivity. So what we did was actually, in addition to the training and holdout set from the AutoQSAR, we held out another group of random molecules to begin with from the original 400. And so there's another CSV file, which again, I'll pull up here just to show you outside of Maestro. It's this set of data, which we randomly chose. I think it's 40 structures from the original data set, which again, we know they're ionic conductivities, but AutoQSAR has never seen these structures, right? So it's only seen the structures that we fed it originally. And so we're going to take these structures and try and predict their ionic conductivities and see how they compare to the known experimental ionic conductivities. So this would be sort of another form of validation. And then you could imagine, taking a next step where you take some completely new structures and try and predict the conductivity values. So I'm going to just collapse this group and we're going to import that second CSV. So again, we're going to go to File, Import Structures, and there's a second CSV file available, which is the test CSV. And again, that's just the CSV that I showed you open on the screen a moment ago. So these are the 40 structures that we held out. So I'm going to click Open. Again, I'm going to import the smiles, and I'm going to title them by their index in the entry list, and I'm going to click OK. So now, again, you've got your 352 structures up above, which in my case, I collapsed. And then down here, I have 40 more structures. And I'm going to group these as well. So I've highlighted them all. They should come in all highlighted, but if you need to yourself, you can just use Shift-click and get them all highlighted, right-click, and group them. And I'm going to group it and call it the test set. And I'm going to put it at the end of my project table and click Create Group. And so now I have a second group here, which is my test set, which has my 40 structures. And you can look at them. And so these come from the same data set. So they're not totally novel structures, and they're in the domain of the ML model, which is really important. And we'll look at the prediction values, and you'll see that they get domain scores. And so you always want to be mindful about the types of structures that you then attempt to use your ML model on, and how far you can extrapolate. So we have these 40 structures. So what we're going to do is we're going to select them all, and we're going to go back to the AutoQSAR panel one more time. So let me open it up here. And you need to have already done this view model and make predictions. So you have to have your QZip loaded in, because that QZip is what AutoQSAR is going to look to make predictions. It doesn't matter which row in the table you have here selected, because we're going to use a consensus prediction, which is going to use all of these models. But we're going to come down here and now use the make prediction capabilities of the tool. So first, it asks you which structures do you want to make predictions on. And so again, that's why I've highlighted these 40 structures. You want to make sure that you have them selected here in the entry list. The model that I'm going to use is the consensus prediction. The property that's going to be fit, it's grayed out here, but it's the conductivity, and it knows that's the model, that's the property that these models were trained for. And then you can name the property that it's going to output. And so I'm going to call this predicted ionic conductivity. And so that's just what those properties will actually be named when we go to look at them afterwards. And so this will be, we can name this job whatever we want, QSAR test ionic conductivity. And then again, you want to pick a resource to use to run the job. And so localhost is fine. You can run this job on one processor. Click save, and I'm going to click run. So I'll just recap there what I did, and then I'm actually going to run this job. So I imported the 40 additional structures, which are available from going to File, Import Structure. They're a CSV file there in the provided data. I made sure that I had already loaded in my QZip file, which we were analyzing earlier. And then I chose to use all the models. I named the property that I want to predict. I named the job. I picked a resource, and I push run. So now I'm actually going to run this job because it takes about a minute, I think, maybe less than 3. So I shouldn't waste too much of our time here. And so you can actually see how job running looks. So you see this gear starts to turn when I push run. I can close the panel, and you can see this green dot that I mentioned before. So whenever you have a calculation running, you're going to see a green circle here in the job monitor, and you can actually click on job monitor and you can see the status of any of your running jobs. So this QSAR test ionic conductivity is currently running, and there's a green circle. And I'll give it a minute, and eventually that green circle should turn to a green check when the job finishes. If it takes more than a minute or 2 here, again, the data is available in the directory that's provided through nanoHUB. So so long as you set the correct working directory, you should be able to view these results, even if they don't come back super fast. All right, and that's it, the job finished. So you see the green check. And then in this case, when the calculation finishes, a new group is added to your entry list. And so this group is called this QSAR test ionic conductivity -out 40. And it just has the same 40 structures that we loaded in for this test. But now the difference is that each of these structures has a new property associated with them, which is the predicted value of their ionic conductivity from the ML models that we generated with AutoQSAR. And so how can I see those predictions? Well, I can go back to the table like we did earlier. And so this column, which is conductivity, this column is the experimental data. But there should be a new column. So I scroll across, and here you can see the predicted ionic conductivity values, and here they are. for each of these 40 structures. So these are the values themselves. So you could look at them sort of structure by structure and view them in the workspace and see, okay, you know, the structure here has a very high prediction and so forth. But in addition to the ionic conductivities, we also get two other parameters back. We get the standard deviation on those predictions, which is useful. And then, as I mentioned before, we get a domain score, which you can use to see sort of like how far from the sort of training structures do these test structures look structurally. And so this can give you a feel for like, are you trying to make a prediction too far outside of the original data set? Okay, so the last thing you might want to do, because in this case we have the experimental data, is just take a plot of these predictions versus experiment. So that's something we can do here in the project table. So I click on this whole group again. This is the output group from the calculation, and we have a tool here for generating all sorts of plots. I click Manage Plots. And I click New Scatter Plot. This takes you into our scatter plot editor tool. This can be used to create any scatter plot of any of the properties that you have in the project table. And so in this case, we'll make the x-axis the known values from the NIST database. That's the ionic conductivities. And I'll make the y-axis our predicted ionic conductivities. And here's our output plot for those 40 structures. You can see, it passes the eye test quite good. But in addition, you could add a best fit line, which will plot right here on your scatter plot. You can see a pretty good R-squared value of 0.84. Again, these are 40 structures that were not fed to AutoQSAR for the initial training. And so these were completely held out, and we can see that our ML model does a pretty good job of predicting the ionic conductivities here for these held out ionic liquids. Okay, so I'm gonna stop there and go back and just show you one or two more slides about sort of next steps. And again, feel free to rewatch this recording. And then we also have the written version of tutorial in nanoHUB. So you don't need me to walk you through it. You can walk through it yourself or have your students walk through it if they want to go through this exercise, as well as either of the other two exercises that are currently available. And when you're done working in the Schrödinger Material Science Suite here, you can just terminate your session in nanoHUB. So let me go back real quick and just cover, I think, one or two more slides, and then we'll take some questions. So here are some things you could do next if you are feeling inspired from either of these two lectures that Anand and I gave in the last 2 weeks. So first, as I mentioned, we have two other data sets in nanoHUB, which you can feel free to use for educational use. So we have the TADF data set, and we have a homogeneous catalysis data set. You can scan this QR code. It will take you to our group page. If you're interested in all of the capabilities of Schrödinger, so again, we do QM, we do MD, we do machine learning, we do molecules, polymers, crystals, disordered systems. We have online courses which are available for anyone who wants to sign up and do some training. These do come with a fee, but we have, through our partnership with nanoHUB, a 10% discount available for nanoHUB members. So when you register for the courses, you can use nanoHUB 1 at checkout. It'll give you a 10% discount. Here's a link through the QR code to our courses. Right now we have 7 courses available in material science, and 6 of those courses have an entire module on machine learning. The other modules are on, say, quantum mechanics, MD, depending on the course that you choose to take. These tools that we offered today, we'd love for them to be incorporated into the classroom. That's a fantastic use of nanoHUB. And so feel free to just go ahead and use any of these 3 examples already in your classroom. But we also have an additional Schrödinger offering for teaching. So if you're interested in our in-house teaching platform, which can be used for, again, not just machine learning, but any of our capabilities, another QR code there. And then, of course, if you're excited about actually licensing the software, using it for your research, we have academic pricing and commercial pricing. We have institution-wide pricing. You can get in touch with our teams. One more QR code there. So our nanoHUB page, our courses, our teaching, and then licensing software. And with that, I'll stop and thank you for your attention. And Anand is online as well, so please feel free to ask any questions about our capabilities, and we'd be glad to answer them. Thank you.
Awesome. Thank you very much, Michael. Fantastic webinar. So yeah, that was really comprehensive. Went through a lot of things, and of course, there have been a lot of questions, many of which have been answered already. I'm just gonna rattle off some which I think were not answered. Maybe, are these compounds in solution?
So I think ionic liquids are typically, standalone, right? And they're these ionic conductivity values are probably not measured in a solution, but I'd have to check the NIST paper
Right.
to be sure.
Yeah, I think this was partially answered, but you're dealing with ionic conductivities in liquids. I'm interested in ions within clouds. Can the system deal with this?
Within clouds, you said? Yeah, I'm not exactly sure what they necessarily mean by clouds, but yeah, happy to hear a little bit more and answer that. So whoever asked it, feel free to flesh it out a little more. Thank you.
Could you use Schrödinger to build a data set? I think Anand answered that
Yeah,
partly,
that's
but if you want to say something about that.
yeah, that's a great question. So yes, I mean there's a lot of ways to go about it. So this data set comes from the literature. It's smile strings and it's experimental data, but you could also imagine using DFT calculations to generate data on several hundred structures, and then take that data and use it as your property, which you want to be fit by an AutoQSAR model. You can generate descriptors using our software, which you can add in additionally into AutoQSAR to account for. So there's a lot of clever ways to do it. And for that, yeah, definitely watch Anand's lecture last week. He talks about not just these sort of standard ways, but also things like active learning, which are really efficient ways to blend many methods.
Yep, that's right. Yeah, to everybody, please check out the recording. Should be available for Dr. Anand Chandrasekhar's webinar from last week, which covered more broad general things, different types of problems that Schrödinger is working on, different types of data sets, different types of descriptors, active learning, etc. So yeah, certainly do check that out. One more question is about maybe potentially connecting this with the materials project database. Any comments on that?
Yeah, so Anand, maybe you want to comment a little bit about like our periodic descriptor capabilities and our connections with materials project.
Sure. If you have once you get the API access from Materials Project website, you can paste in the API into the Schrödinger Maestro platform to get direct access to the Materials Project crystal structures. And you can pull specific Materials Project crystal structures and their properties using a particular panel within Maestro. And then once you do that, you can actually generate periodic descriptors using the periodic descriptors panel, which works which basically can featureize all these inorganic systems. And I see, someone asked a question about perovskites. So for perovskites, again, you can also generate periodic descriptors for these perovskites. And once you've generated those descriptors, they can be added to AutoQSAR as an additional descriptor, and you can retrain the machine learning model for periodic systems and perovskites as well. Yeah.
Yeah. I think there was a question about ionic current in perovskite materials. Maybe, yeah, there was some question about that. Okay.
Yeah.
How do you choose how many models to test? I don't know if this was answered.
Yeah, I think I answered it. I mean, it does by default, AutoQSAR does 50 different train test splits. And for every train test split, it loops through all types of models that are available in AutoQSAR automatically. And it selects the best performing models for a particular property. So yeah, I mean, you can change the default number of train test splits to be more than 50 or less than 50. And you can also change the train test split ratio to be something different. I think by default, it's like 70%, 30%. Or 80%, 20%, and you can change that to 90%, 10%, for example. And you can also change instead of top 10 models to output, you can output the top 20 models, for example. And yeah, so all these parameters can be tweaked. I would say there's no harm going with the default parameters first, and then changing it once in a while. Yeah. Someone asked, "Do you have a collection of publications using the software?" Yeah, we can add some references to the AutoQSAR references. I don't have a right now. I don't have a link to paste right now. But if in Google Scholar, if you type AutoQSAR, you will see a handful of publications with our customers there as well.
Is there a transformation on the conductivities of these molecules? Are they negative because they're a log transformation, and does that affect the accuracy of the training?
I think this is a log transformation. Yeah, this is a log transformation, and because I mean sometimes we do a log transformation if the you know the range of values is too broad. So yeah, I'm not sure about the original data set since this was downloaded from NIST database. So I'm not sure about the exact details about how the log transformation affects accuracy of those models. And I think someone is asking if they can upload other data sets into nanoHUB.
Yes.
I don't think that's possible, right, Michael?
Yeah, so right now that's restricted. So if you're interested in actually using the tool for research purposes, you should reach out to Schrödinger about access. And many universities already have access. So it's possible that your institution is already paying for Schrödinger software, and you should check that first. And then if there are other training type examples that people want to see in nanoHUB, we're more than happy to add those. But right now, the tool is really for training and education purposes. If it's to be used for research, yeah, we ask that you reach out to us separately.
Yeah. If you have your own input-output structured data, I mean, you can use the existing, machine learning tools on nanoHUB. If your aim is just to train an ML model, of course, or there are many other resources like that as well. Maybe one final question. Can the model predict atom molecules intercalated within another system of molecules, asking for 2D layered structures with intercalated atoms?
So we have a panel which makes intercalation descriptors. So you can provide it, for example, a lithium ion or sodium ion, and say that find. You can characterize the neighboring sites around the lithium ion for intercalation materials. So that's also part of the periodic descriptors panel. We don't have anything specific for 2D structures. Potentially, it could be featureized with periodic descriptors as well, but I'm not sure.
Okay. Yeah, and there are some questions about like using it for teaching and stuff, which is relevant to a lot of us. I mean, somebody's asking about a downloadable version. I mean, I guess
Yeah, I can comment on that, Arun. So there's sort of three things that you could think about. One is, of course, these three examples. We know it's limited, right? But these are now available, and you should use them for teaching if they're relevant for you. The second is that we do have, if you search our website, something called Free Maestro, which allows you to download the interface itself, which you could use with like pre-stock data for teaching purposes. There's no cost for just downloading that interface and using it to visualize structures, which can be really useful in teaching. And then finally, we have a program which I had a QR code for, but I'll say it again. It's called Teaching with Schrödinger. You can go to our webpage, Teaching with Schrödinger, and this is a platform where we sell access to like a virtual cluster with the entire Schrödinger suite, all of the capabilities. We charge on a per student basis. It's pretty modest fee because it's meant to be used for teaching and training, and that would get you access to like everything, and you can use it on a semesterly basis. So that's called Teaching with Schrödinger. So yeah, please use the nanoHUB tools and request others if you need. Download Free Maestro, or reach out to us about licensing our Teaching with Schrödinger offering.
All right, fantastic. I think we are right about at the end. So thank you very much again, Michael and Anand. This was really amazing. So all the resources are there online. Everybody, please check it out. Reach out to the speakers or to us with other questions. Thank you once again, Michael and Anand. Thank you, Aaron, Amy, Travis, Ale, everybody. Thank you to all the attendees. All right, thank you.